Hello, this is Captain Chaudhari in the series of videos on basic ship stability calculations. Today I am going to do an intermediate compartment bilging on a ship-shaped vessel. Right? So here we are going to find out what is the shift of center of flotation, what is the shift of center of buoyancy. We are also going to find out what is the trim change and what are the final 4.5 drafts going to be. Now the ship sails on an even keel of 9.6 meters. The question is from my book. We are going to do this question on alpha ship. A brief data of hydrostatic particular I have given here for 9.6 meters and 11 meters. Now the ship, which is 171.792 meters long, has got 5 holds, and hold number 2, which measures 26 meters in length, 24 meters in breadth. This is damaged. This hold is cuboidal. That means its dimensions, the whole dimensions, the area of the hold is similar from bottom till the waterline. That is what we assume. There is a double bottom which is of height 1.4 meters below the hold. The center of flotation of the hold is 123.7 meters forward of perpendicular. So we proceed now. Initially, before the vessel gets damaged, the GM is 2 meters and the KM of the vessel, KM transverse of the vessel is 9.876. The KM is 9.876 and GM is 2 meters. So the kg, which is going to be unchanged, is going to be 7.876. So here is the ship. And we have alpha ship. And we have the hold number 2 over here, which is cuboidal. There is a double bottom of height 1.4 meters, which is undamaged. The ship floats on an even keel draft of 9.6 meters prior damage. So we can say that the lost buoyancy is equal to 26 into 24. The height that is damaged is 9.6 minus 1.4. So 9.6 minus 1.4 would give you 8.2 meters. Permeability is 78%. So let's see what is the lost buoyancy. Gives me 3391.1. 3391.1 meter cube. This is the lost buoyancy. Now intact water plane area is equal to total minus lost water plane area. Total water plane area will be, we can find out the water plane area from the TPC. As I told you, 100 TPC divided by 1.025. 100 TPC divided by 1.025 is the total water plane area. From here, the lost water plane area is 26 into 24 into 0.78. So TPC 3424 divided by 1.025 equals minus, in the bracket, 26 into 24 into 0.78 gives me 2853.77. 2853.77 meters square. So the sinkage is equal to lost buoyancy upon intact water plane area. The lost buoyancy is 3991.1 divided by 2853.77. This gives me 1.398. So we can take approximately the sinkage as 1.4 meters. So that will help us do the calculation, understand the calculation better with the round figures. So we say that the final draft is 11 meter. Final draft is 11.00 meters. Now there are a lot of things to be done because it's a ship-shaped vessel and we are doing it by constant displacement method. Now, one of the first things that should be found out is what is the shift of center of flotation. Now, if we look at the plan view of the ship, say this is the plan view of the ship, and suppose the hole number 2 is over here. It seems suppose this is aft perpendicular, from the center of flotation till the aft perpendicular, it is 100, from the centroid of the hole till the aft perpendicular, it is 123.7 meters. And if we look at the final water line, the LCF is 82.2. LCF is 82.2. So what is the distance from the center of flotation of the ship to the center of flotation of the hole? That is 123.7 minus 82.2. That gives me 41.5 meters. So from here to here, it is 41.5 meters. Suppose we want to take the moment of areas to find out what is the shift of center of flotation. Our usual calculation is the total area multiplied by 0, because I am taking the moment of the total area about the own centroid. So distance from the area centroid to the own centroid, that is from own centroid to the reference axis, would be 0. So the first expression is A into 0. This is what we do in all intermediate or end compartment bilging calculation of FF1. So OA into 0 minus, this area is 26 into 24, and the distance from centroid to here is 41.5, and there is a permeability of 0.78. Divide by intact water plane area. Intact water plane area is 2853.77. So what we get is 26 into 24 into 41.5 into 0.78 equals, divided by 2853.77. That gives me 7.078. This is 7.078. We'll keep writing the details here. The intact water plane area is equal to 2853.77, and the FF1 is equal to 7.078. Now next we want to find out what is the shift of center of buoyancy. There is a vertically upward shift of center of buoyancy, and there is a shift of center of buoyancy away from the damaged compartment. That means center of buoyancy moves outwards. So in the final condition, now that we have got FF1, the final LCF1, because the center of flotation has shifted aft, so the new center of flotation will be the final center of flotation, that is 82.2 minus the FF1. So that gives me 75.122. 75.122 meters. That is the center of flotation in the final condition. Now if we look at the ship submerged, and if we assume, just for making the calculations a little simpler and without appreciable change of accuracy, let us say that the ship sinks bodily. And if the ship sinks bodily, now can we say that we have lost the buoyancy here, right? And the buoyancy is gained at this point. We can say the half of this lost buoyancy height is 4.1, from here to here is 8.2, so half of the height is 4.1 plus 0.7, so 4.8. So 3991.1 into 4.8. So I hope you understand the total height of lost buoyancy is 8.2, half of that is 4.1. Now the sinkage is 1.4 meters, half of the sinkage is 0.7, so 0.7 plus 4.1 is 4.2. 8. So that means we lose the buoyancy here, we gain the buoyancy here. The distance, vertical distance is 4.8 meters. If we divide this by intact underwater volume will be the initial underwater volume. The initial underwater volume is given by 28715.6 divided by 1.025. So this will give me as to what is the vertical displacement of the center of buoyancy. So this is 3991.1 and that is 0.684. This is 0.684. The original KB was 5.108, and as we know the golden rule in any bilging situation, the center of buoyancy always moves upwards. So from the original KB 5.108, the center of buoyancy being going upwards by 0.684, the new KB or KB1 will be 5.108 plus 0.684. That gives me 5.792. 5.792. That is the new KB. So this we have found out the shift of center of buoyancy in upward direction. There is a shift of center of buoyancy in longitudinal direction also, and we are going to find out. So this is the shift of center of buoyancy in upward direction by 0.684 meters. The center of buoyancy is also going to move away from the damage. That means, now as you know, the center of flotation has shifted upwards by amount 7.078, right? That is because the water plane area is damaged over here. So new center of flotation, new LCF will be reduced, and new LCF is 75.122. That means there is a new position of center of flotation here, and the distance is 75.122. Now can we say that we have lost the buoyancy here and the buoyancy is replenished in aft direction? The longitudinal distance between the loss of buoyancy and replenishment of the buoyancy is like this position is 123.7 meters from aft perpendicular, and the point where the buoyancy is replenished is 75.122. So the distance between them is 123.7 minus 75.122, that is 48.578. So this distance is 48.578. So we have lost a buoyancy, and that lost buoyancy is equal to 3991.8, and longitudinally the lost buoyancy is replenished at this point, and that distance is 48.578, right? So lost buoyancy is 3991.8, and we have lost the buoyancy over here, and we have gained the buoyancy at this point. The distance between them is 48.578. So lost buoyancy multiplied by the distance to the point where the buoyancy is replenished, divided by intact underwater volume, and that is 28715.6 divided by 1.025. So the longitudinal shift of center of buoyancy is 3991.1 into 48. That gives me, this is 6.921. So the center of buoyancy has shifted in aft direction by an amount equal to 6.921 meters. So center of buoyancy is shifted aft by an amount 6.921 meters. This is instrumental in causing the trimming moment. And we have trim change. The formula is trim change upon LBP is equal to BB1 upon GML. So next we are going to find out what is the GML, and GML can be found if we know the BML. To find out the BML, the formula is the BML is equal to residual moment of inertia about athwart ship axis passing through the new center of flotation divided by intact underwater volume. Let's look at the ship in a plan view, and at the water level, and let's say this is hold number 2, cuboidal hold, and let's say this is the new center of flotation F1. This is the athwart ship axis, and this is the axis, athwart ship axis passing through the centroid of the hold. Now, to find out the moment of inertia about athwart ship axis through center of flotation at 11-meter draft. So the question is, can I find out the moment of inertia about an athwart ship axis passing through the center of flotation at 11-meter draft? The answer is yes. At 11-meter draft, I know what is the KB. For 11 meters draft, the KB is 5.871. 5.871. And I know Km longitudinal is 205.87. So BML at 11 meters is 205.87 minus 5.871. So that is 199.999. 199.999. 199.999 meters. That is a BML. But BML is equal to the moment of inertia about the athwart ship axis upon V at 11-meter draft. So this is BML. So can I say that the moment of inertia about the athwart ship axis is equal to 199.999 multiplied by V? And what is V at 11 meters? V at 11 meters is 3355.3.1 upon 1.025. So let us find out the moment of inertia. 199.999 into 3355.3.1 equals divided by 1.025. That gives me 6546919. This gives me 6546913. So I don't want to consider the digits after decimal. So I get 6546913 meter raised to 4. Now I will write down this value here. So moment of inertia at 11-meter draft, the athwart ship axis, is 6546913 meter raised to 4. Now that is the moment of inertia at 11-meter draft about the center of flotation. So what is the moment of inertia about the new center of flotation? That will be given by, so moment of inertia about new center of flotation is going to be 6546913 plus AD square. Water plane area at any draft is TPC into 100 divided by 1.025. So what is the TPC at 11-meter draft? TPC at 11-meter draft is 34.65. It is 34.65. So we will say 3465 divided by 1.025. That is the area 3380. 3380.49 and multiplied by d square. What is the d? D is the shift of center of rotation, is 7.078. 7.078 0.078 whole square. So let us solve this. 6546913 plus in the bracket 33 3380.49. So 6546913 plus 338 gives me 6716269, right? And from here we need to minus the loss of moment of inertia because of the hold. So the moment of inertia, so if we talk about the lost moment of inertia, the moment of inertia about the one axis, loss of moment of inertia about the one axis is 24 into 26 cube upon 12, right? Assuming that the permeability is 1. Now what is the distance from centroid to the center of flotation? Now lost moment of inertia is loss about the one axis plus AD square. So AD square is 24 into 26 into D square. D square is 48.578 square. But the loss has to be multiplied with 0.78. So let's do this calculation. (24 into 26 into 26 into 26 equals divided by 12 gives me 35152 35152 plus 78. So the total loss moment of inertia is 1175991. So this has to be minus from the total moment of inertia. So that is what I will do, minus 6716269. That gives me 5540277. So what I get is 5540278, and this divided by intact underwater volume, that is 28715.6 divided by 1.025 should give me the new BML. So new BML will be this value 6, and that is 197.759. 197.759. So 197.759 is the new BML plus 5.792. I get KML. So KML is equal to 203.551 and minus kg. Kg is 7.876, right? That gives me GML. So the value of GML is 195.675. So trim change equal to LBP into BB1 upon GML. LBP is 171.792, and BB1 is 6.921, 6.921 divided by GML, that is 195.675. So 171.792 into 6.921 equals divided by 195.675 gives me trim change is equal to 6.076. 6.076. That is the trim change. TRA will be this value multiplied by LCF. The new LCF we have is 75.122. So this value into 75.122 will give me a product 456 something divided by LBP. LBP is 171.792. That gives me 2.657. 2.657, and this when I subtract from the total trim change, that is 6.076, I get 3.419. 3.419, that is TRF. So our draft after sinkage is 11 meters, and we have a damage in the forward part. So the forward draft is going to be 11 plus 3.419, that is 14.419 meters, and the aft draft is going to be 11 minus 2.657, and that is 11 minus 2.657, that is 8.343. 8.343. So you've seen the trim change compared to the even keel posture is 6.076 meters. There is damage forward, so forward will go down, and there is a tremendous increase of draft. The forward draft is 14.419 and the aft draft is 8.343 meters.